terms of sampling distributions. So this leads us to the central limit theorem, but let me go one more step. So if I take n equals 3, alright, I've got outcome 0, 0, 0, 0, 0, 1, right? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right, and we've got 2, 4, 6, 8 different outcomes, and this boils down to distribution of what we have. Let's talk about the number of x's here, right? Right, the number of outcomes. The number of ones, for instance, 0 ones here, 1, 1, 1, 1, 2 ones, 1, 1, 2 ones, 2 ones, and a 3. Okay, or with each the same probability. All right, probability each of these is 1/8. But writing it more neatly, if I can do that here, that we have x being either a 0, 1, 2, or a 3. Okay, and the probability of a 0, there's only one way of doing that. It's 1/8, same as a 3. There's only one way of doing that. There are ones, there's 1, 2, 3 ways of doing that, so that's 3/8. And similarly then 3/8, right? So that gives us our probability distribution of 1. If we talk about averages, x bars, right? So it's, in a sense, we'll divide each one of these by our sample size of 3, so there will be 0, 1/3, 2/3, and 1. And the probabilities remain the same, right? 1/8, 125, 3/8, 375, 375, and again 1/8. Alright, so this is our probability distribution for x bars, and hopefully some of you will at this point understand that this is nothing more than the binomial distribution, where n is 3 and p is equal to a half. Okay, and all we've done to go from the binomial to this distribution over here is divide everything by the n of 3. Okay, we just scaled the binomial distribution, just like we have scaled earlier when we talked about the normal distribution. We can scale them. Okay. Alright, so, and we can go on and on like this. So, since my simplest case here for the population, zeros and ones, is just the binomial situation, and we know that for a large enough n we can approximate the binomial with the normal. And I think at that video I also said that there is a sort of general case of the binomial, the big brother of the binomial, if you like, called the multinomial. Instead of having 2 outcomes, you can have 6, 8, 10, 50, a million different outcomes on your population. And therefore the multinomial also can be approximated with the normal under certain circumstances. Okay, and that leads us to the concept of the central limit theorem. In the normal layman's terms, this would be the law of large numbers, in a sense. The law of large numbers is actually never specified properly, but let's do it here for the central limit theorem. Alright, and I'll do it as follows. For samples, of size little n taken from any population where any is important. Population does not have to have a shape, does not have to be normal, for instance. Doesn't have to be anything. With a mean mu and standard deviation sigma. It's just definitions. Then the sampling distribution. Right, so this is the probability distribution of all possible sample averages. So the sampling distribution of the sample average or sample mean is, for certain situations or certain conditions, approximately normal. We'll say for n greater than 30, roughly. With a mean equal to mu and standard deviation of this sampling distribution. Right, we're talking about the mean and standard deviation of the sampling distribution. Sigma sub x bar equals sigma population standard deviation divided by the square root of n, the sample size. Okay, so this is the central limit theorem. But the aspects of this are important, not just learning this off by rote. Alright, so if we take sample size 30 and above from any population, any shape if you like, any mean, any standard deviation, then the mean of this distribution of all possible sample averages is equal to the population average, and the standard deviation of this distribution of all possible sample averages, sigma sub x bar, is sigma divided by the square root of n. Okay, and that's very important. So doing it roughly, we have a distribution of the population, and let's make some ugly shape. Probability under this distribution is 1. As long as we have samples, say, greater than or equal to 30, 30 above, it's not a magic number yet, then the mean of the distribution of these x bars is approximately normal. Sorry, the distribution is approximately normal. The mean of the distribution is equal to the population mean mu. Okay, and the standard deviation of the population is sigma. The population, so the standard deviation of the sampling distribution sigma sub x bar is sigma divided by the square root of n, which is always smaller than the variance or standard deviation of the population. As before, these concepts are all very important to the understanding of the really, owning the concepts of probability and sampling in your heart. But to be honest, they're not the easiest thing in the world. I'll make one more effort to make sure that you know that a sampling distribution is not equal to a sample distribution. That the term sample distribution is actually not used. A sampling distribution is for all possible, say, sample averages, or just say samples. Alright, and a sample distribution would be, if there was such a term, for one sample. These are not the same. I'm doing that, making this distinction here, hopefully clearly, to make sure that you understand that for the sampling distribution we'll talk about mu and x bar, where this mu is actually mu sub x bar, is very different than x bar and s. Alright, x bar the sample average, s the sample standard deviation. These are very different concepts, different bits of notation that we'll use. Okay. Alright, so this is the end of this video, and in the next video we'll talk about using sampling distributions to calculate probabilities.